Okay, so this lesson is about orthogonal sets and orthogonal projections. So we're going to continue to talk about what it means for two sets to be orthogonal. So here I've got vectors u1, u2, u3, and x. So I'm not even thinking about x right now, right? I want to show that u1, u2, and u3 is an orthogonal basis for R3. So ignore the word orthogonal, right? To show that something is a basis for R3, what is the definition of a basis? It spans the entire set and it is linearly independent. Okay, so I have so far two things I need to show. Spans R3, two linearly independent, right? And then we have the word orthogonal. So an orthogonal set means that every vector in the set is orthogonal to every other vector in the set. So I have to show, thirdly, that u1 dot u2 is 0, u1 dot u3 is 0, and u2 dot u3 is 0. So I made every possible pair, right? And showing that the dot product is 0, that shows that the vectors are orthogonal. All right, so to show something's a basis, I need to show that it spans R3 and is linearly independent. Spanning R3, remember we're looking for pivot in every row. And linearly independent, we're looking for a pivot in every column. So I'm just going to take my vectors u1, u2, u3, put them in a matrix, row reduce, and if I get the identity matrix I3, then I'll know that this is a basis. So 1, 0, 1, negative 1, 4, 1, and 2, 1, negative 2. This does come out to 1, 0, 0, 0, 1, 0, 0, 0, 1. So yes, it is a basis. Next thing I have to find out is it an orthogonal basis? Is it a special kind of basis where every vector in it is orthogonal to the others? Okay, so u1 dot u2. See, that's negative 1. Oops. Nope. u1 is 1, 0, 1. Dotted with u2, which is negative 1, 4, 1. So that's going to be negative 1 plus 0 plus 1 is 0. Check. u1 dotted with u3, 1, 0, 1. Dotted with 2, 1, negative 2. That's going to be 2 plus 0 minus 2, which is 0. Check. And then last one, u2, negative 1, 4, 1, dotted with 2, 1, negative 2. So I get negative 2 plus 4 minus 2, which is 0. Check. All right, so it is an orthogonal basis. It's a basis and it's an orthogonal set. If I normalized those three vectors, u1, u2, and u3, what would the name of that set be? Instead of just plain old orthogonal, it would be, anybody remember from the reading? It's ortho, right? Because it's still orthogonal, but now they're all normalized. All the vectors have been made into normal vectors, so it is orthonormal. Ortho for orthogonal, normal because we normalized the vectors. Okay, I want to express x that I was given, the 8, negative 4, negative 3. In fact, I think I'm going to grab these vectors and put them on the next page so we can easily refer to them. Okay, so I want to express x as a linear combination of the u's. So I'm going to do it two ways. One of which we could have done like in the first or second week of class, right? I'm just saying, what weights should I put on U1, U2, and U3 to make X? Okay, so say X is C1, U1 plus C2, U2 plus C3, U3. What weights C1, C2, and C3 should I put on the vectors U1, U2, and U3 to create X, right? So what do I do? How do I solve this problem? Oh, that'd be augment with the X. Yeah, we got it. So I'm just going to put each of my U1, U2, U3 in here. So I'm saying, what X's do I put on those to build the 8, -4, -3? And this row reduces to 1, 0, 0, 0, 1, 0, 0, 0, 1, augmented with 5 halves, -3 halves, and 2. So these are my weights. These are my C's. C1, C2, C3. That says C1 is 5 halves, C2 is -3 halves, C3 is 2. All right, so this is not new. But there is another way that we can find that same C1, C2, and C3, and may or may not be quicker, but it's another way. But it only works if you have an orthogonal basis. So this next method is only if you have an orthogonal basis, which we do. That's what we showed in the first part of the problem. So it says there's this formula that you can use to calculate the weights. C sub j, the jth weight, is going to be y, or in our case x. X dotted with u sub j over u sub j dotted with u sub j. So C1 is going to be x dotted with u1 over u1 dotted with u1. So my x vector is 8, -4, -3. U1, that's a given, it's 1, 0, 1. And then over 1, 0, 1 dotted with 1, 0, 1. So this comes out to 8 times 1 plus -4 times 0 plus -3 times 1 is 5. And 1 times 1 plus 0 times 0 plus 1 times 1 is 2. 5 halves, which is the same thing we got in the row reducing method. And then you would just repeat for C2 and C3. Good? Okay.
So is there a situation where that might be easier?
Maybe if you're looking for a lot of weights, like row reducing is a very time-intensive process, right? Whether it's you or a computer, right? Computer time is much faster than our time, but when it's really, really big, you don't want to waste computing time. So this might be faster. In computing power, yeah. In general, I don't know. in what you're going to be doing in this class, probably not. Okay, so now we're going to talk about orthogonal projections. So this example that we're going to do is in R2 so that I can draw for you what we're looking for, but the formulas that I'm going to give you apply to any Rn. Okay, so we're looking for the orthogonal projection of y onto the line that goes through the vector -4, 2 in the origin. And then we're going to write y as the sum of two orthogonal vectors. One's in the span of you and one's orthogonal to you. Like, what, right? Okay, so this means I'm going to draw a picture of what they're discussing. So I need 1, 7, and negative 4, 2 are my sort of key points here. 1, 2, 3, 4, 5, 6, 7. Yeah. Yes, I believe that it is. Component of y that's perpendicular to u. That's part of the question. Yeah. And then you want the other component as well. Yeah, in the direction of u. Yeah. Okay, so 1, 7. Oh, different color. Okay, 1, 7. That's my y. All right, and I'm going to project that onto the line through negative 4, 2. 1, 2, 3, 4, 2. And the origin, so I'm going to draw this as best I can. All right, so the orthogonal projection means I'm going to take y and project it onto the line orthogonally, right? So I'm going to drop a perpendicular from y to the line I just drew. Oh, I want a different color than that. Let's do this one. That looks almost exactly the same. Oh well. All right, so I've now taken y and projected it onto the line u orthogonally, meaning I dropped a perpendicular. So now I want to find two things. I want to take y and I want to write it as the sum of two vectors. One's in the span of u, meaning it's on the green line, and one is orthogonal to u, meaning the dashed line I just drew. So there are two things I'm looking for. Highlight them. I need this vector and I need this vector. I'm trying to break down y into its components, one perpendicular to u and one on u. All right, so let's just see if we can guess. So this one that's on u. So in span of u. Just the way I drew the picture, it looks like maybe negative 2, 1. And we call that particular point y hat. Yeah. Not y, I'm using u. U is one of their vector bases. Yeah. And then we're going to use an orthogonal one to u as the other vector in the basis. Yeah. All right, and then the one orthogonal to u, we call that one z. This is just standard notation that your book introduces, y hat and z. So z is this highlighted vector that's the dashed line. So if I want to know, if I want to get from this point to y, like add these two vectors, this vector is actually, let's see, 1, 2, 3 to the right, and up 1, 2, 3, 4, 5, 6. Right, so that would be 3, 6. To get to y. This is just a guess based on our picture. All right. Now your book gives you several formulas that you can use to calculate y hat and z. Well, one formula for each. All right, so your book says you can calculate y hat by taking y dot u over u dot u times u. These are all vectors. Okay, so y, that is 1, 7. 1, 7 dotted with u, which is negative 4, 2, over u dot u, negative 4, 2 dotted with negative 4, 2, times u, which is negative 4, 2. And this isn't a dot product here because this big fraction is going to be a scalar. So when I simplify that fraction, I end up with negative 4 plus 14 is 10. And then 16 plus 4 is 20. 10 20ths times negative 4, 2. So that's a half times negative 4, 2. So I get negative 2, 1. Which is what we estimated from the picture. Negative 2, 1 for my y hat. And then my z. So let me need another color. Black. This. Okay, this right here, that's y hat. Okay. And then this piece right here, that's z. And z you can calculate by doing y dotted with the y hat you just found, right? Perpendicular to y hat you just found. Okay, so y is 1, 7 dotted with y hat, which is negative 2, 1. So you get negative, that can't be right because it's a scalar. What did I do? Oh, it's y minus y hat. Right. Y minus y hat. Okay, 1, 7 minus negative 2, 1. So I get 3, 6. My z. So I found the y hat and the z. The goal was to write y, my original y, as a sum of y hat and z. So then I'm going to finally write that as a sentence to answer the question. So my y, 1, 7, can be broken down into the sum of y hat and z. Negative 2, 1 is in the span of u, and z is perpendicular to u. So like I said, these formulas for y hat and z, they can apply to larger dimensions than R2, but I wanted to be able to show you the picture of what we were actually doing in R2 at least.